hello everybody. So last time we started this second part of the chapter, the solution stoichiometry, and there were some images missing from the PowerPoint. So I just wanted to go through and show you some of those images before we move on. We're going to talk about acid-base reactions. We're going to talk about some redox reactions. So this first slide that was missing is a picture of an ionic versus a molecular substance dissolved in water. And on the left we have ionic. On the right we have a molecular substance. On the right it could be any sort of like NaCl, anything that has a positive and negative charge. You can see that the water breaks up the solid. Here's the solid, I just kind of circled it. And then I can highlight here the ions that are interacting with the water. They form this ion-dipole interaction. I won't really be testing you on that just yet. We're going to do a whole bonding chapter. And then on the other side, on the side B over here, we have a molecular, in this case a liquid in a liquid. So this is methanol. And you can see that that doesn't break up into ions. So on the left we would have an electrolyte, and on the right we would have a non-electrolyte. So I also talked about a conducting electricity. Well, what does that look like? So if we scroll down a little bit here, this is showing you a picture of what it looks like where we are conducting electricity. So in the first left pane over here, we have no ions, and so the light bulb would not light up. We have a few ions if we had a weak electrolyte, something like a weak acid. And on the right here, we have many ions, a strong electrolyte. Now just to go through, there was another slide missing. This talks about the difference between strong electrolyte, weak electrolyte, and non-electrolyte. And so if you're ionic, you're always a strong electrolyte as long as you dissolve and you're soluble. If you're molecular, you could be a strong electrolyte if you're a strong acid, but you could also be a weak electrolyte if you're a weak acid or base. And then you could be a non-electrolyte if you're any other type of molecular substance. So if we look at the strong acids and strong bases, here's the list of strong acids and strong bases. You know, we went through this. We talked about brickle, no, so, clo. And this is just a quick way to remember all of the different strong acids. And then the strong bases being the group 1 hydroxides and some of the heavier group 2 hydroxides. Another thing that we talked about in class and also in the notes were precipitation reactions. And so here's a precipitation reaction. And this shows, in this case, the person has in the beaker in their hand, they have Ki. In the beaker that's sitting on the table, there's PbNO3 And when you go and you mix them together, you form this really nice, bright yellow precipitate that eventually will sink to the bottom. So, you know, something that you may want to do is write out a net ionic equation for this. We did this in class at this point. So one of the things that you could do is write out what the net ionic equation is. We can talk about that tomorrow. Okay, one last thing that was missing was the solubility chart. And if I zoom in on that, here's the solubility chart. This didn't come out as great as I would like it to. It seemed to be cut off. But to show you, on the left here, these are soluble ionic compounds. Let's highlight them. So if one of the compounds contains one of these ions, nitrate, acetate, chloride, bromide, iodide, sulfate, if those substances contain those ions, they will be soluble. The issue is that sometimes you can combine some of these with other ions, the positive cations, and it will cause them to be insoluble. That's the case for the halides, where you had silver, mercury 1, and lead plus 2. In those cases, when you combine those with chloride, bromide, or iodide, you get a substance that is a precipitate. It is insoluble. With sulfate, you can add to the list strontium and barium. Silver sulfate's pretty insoluble too, but they don't list it here. And then there's some substances that are always insoluble. These substances are always insoluble. Sulfides, carbonates, phosphates, and hydroxides. Now there are exceptions to those. The exceptions are basically always the same. They're ammonium ions and alkali metals. And then the sulfides and the hydroxides also have calcium, strontium, and barium in there as well. You should know these general solubility rules. You need to memorize them. You will not have a table listing the solubility rules when you take the test or when you take the IB or AP test. So we talked a lot in class about precipitation reactions and about writing net ionic equations. So what I'd like you to do is I'd like you to take a couple of compounds and put them together and see if there's going to be a precipitate or not. So why not, for example, let's try some of these. Let's try something like Ki plus AgNO3. So go ahead and try that out. Now we also did net ionics in class. Let's try out writing a net ionic for this too. Let's see how you do. Sometimes you'll just be given the words, of the formulas, but only in word format. So you might be given, something like this, where they give you barium chloride and sodium sulfate. So again, transform this into the symbols, and then write out what the reactions are and write out what the products are. Let's see how you do with this. Let's do one more. Let's do potassium chloride and lithium hydroxide. So for each of these, figure out what the products are. Figure out if a precipitation occurs. Maybe I tricked you. Maybe no precipitation occurs for any of these. But let's see. So normally I do more practice here with more precipitations. We could try one like this. We could do magnesium nitrate plus sodium hydroxide. We could also do maybe something like iron 3 sulfate plus lithium hydroxide. Okay, so, here are a few precipitation reactions. Try them out. Try and write them as net ionic equations. Now, we did this in class, but just as a quick refresher, if I were to take, something that might precipitate, let's say that we had calcium chloride and we reacted it with sodium carbonate. Well, if I wrote the products of this, I would get calcium carbonate and I would get sodium chloride, and I could balance this with a 2 in front. Now, if I know my solubility rules, then I will know that this calcium carbonate is solid, and so a precipitate has formed. But now I need to see, well, what are the ions involved in forming this precipitate? And that's where doing a net ionic equation is so important. So when I do my net ionic equation, I break everything that's soluble, that's aqueous, and that forms ions up into the ions that they form. So I would break the calcium into its +2, and the chlorides into their -1s, and the sodiums into their +1s, and the carbonate into its -2. On the product side, things that are not aqueous, like the calcium carbonate solid, would stay as a solid. And to that, I would add my ions. This is an ionic equation, but it's not a net ionic equation. I need to cross out things that are spectators. So the chlorides would cross out, and the sodiums would cross out, and you would be left with calcium +2 plus carbonate -2, yielding calcium carbonate, solid. I'd like you to go back to all of the equations that I set up here and write out the net ionic equations. Remember, the advantage to doing a net ionic equation is that it really highlights what ions are involved in forming the precipitate. That's all that we really care about. We want to see the ions that are involved in forming the precipitate. Now let's talk a little bit about acids and bases and how they react. There are different definitions for acids and bases. The two main ones that you really need to know are the Arrhenius and the Bronsted-Lowry. You might remember these, hopefully you do, but the Arrhenius definition, it says that acids form H+ ions in water, and bases form OH- ions in water. And so an acid could be something like, HCl, and it would form H+, and it would form Cl-. And a base would be something like NaOH, because when I put it into water, it forms Na+ and OH-. And this was a useful definition at the time, and it could still be useful. Most acids do form H+, and most bases do form OH-. But when we want to look at how these substances react and interact with the water, we need a better definition. And so Bronsted-Lowry, their acid, says that the acid is a hydrogen or an H+ or a proton donor, and a base is an H+ acceptor. And the two go together. And so for an acid, you'll have your H+ being donated, and it will look something like this. If I were to have my HCl, it would now have to react with something like water. And when it reacts with the water, it will form H3O+ and Cl-. Well, how did it do that? Well, the H was donated from the HCl to the water. It became H3O+. It left the Cl- behind. In this case, the HCl acted as the acid, and the water acted as a base. And we don't think of water as a base, but according to Bronsted-Lowry, it can act as a base in this case. How does this look on the molecular level? Well, here they're showing water now reacting with another substance, in this case ammonia. The H2O, here's my H. It's being given to the ammonia. In this case, the water acts as an acid. It's donating its hydrogen to the ammonia, and this acts as the base. They have a name for that. It's called being amphoteric or amphiprotic. Now we could do a series of Bronsted and Lowry acid and base reactions. For example, if I were to give you something a little bit, less specific here or less, obvious, something like if I were to give you HNO3 and then also give you something like HSO4-. If I put these two substances and they're both aqueous and they're in water, well, then we could have a reaction taking place. We could have H2SO4 forming, and we could have NO3- forming. So go ahead and list which one's the acid, which one's the base. Hopefully you got that HNO3 is the acid. It gives its hydrogen over to the hydrogen sulfate ion. That hydrogen sulfate ion acts as a base and accepts it. Now, you could also have a neutralization reaction with acids and bases. And this is where you have an acid plus a base, and they react and they form salt and water. So we did some examples in class for like this. So here are some examples like HCl plus NaOH, and it yields NaCl and H2O. How would this look net ionically? Take a second, pause the video, try it out. Well, if you got H plus and OH minus forms H2O, you got the correct answer. Try another one. How about acetic acid plus potassium hydroxide? So take a second again, pause the video, try it. If you got this, that's the correct answer. If you're not sure how I'm doing this, please come talk to me or we'll discuss it in class a little bit more in detail. Now, when we do an acid-base titration, and we'll do one later on in the year, how do we know when we're completely neutralized? Well, we use an indicator. And this indicator here is called phenolphthalein. Phenolphthalein will turn from colorless when it's an acid to pink when it's in a base. We'll talk about the math behind these acid-base titrations and what the acid-base reaction looks like a little bit later. One last thing I want to do with you is acid-base and gas formation. There's two main ions that you can react and will act like a base when they react with acid, and one of them is a sulfide ion. And so what happens here is this sulfide ion will replace the chloride ion, and you'll end up with this, H2S and Cl-, and this H2S is a gas. Another reaction that occurs and forms gas is where you have a carbonate. So if we take this HCl and we react it with a carbonate, this will actually form this intermediate, H2CO3 and calcium chloride. But what happens next is interesting. This carbonic acid that forms breaks down into CO2 and H2O. Now if you combine these and write the net ionic, you get this. You get H plus. If we consider this a solid, we can keep it together. It'll form calcium ion, CO2, and H2O. Now I went through this quickly. Take a second, try it out on your own. Break them up into ions, cross out the spectators, get it to work so that you get an overall net ionic equation. Here's my gas, my CO2. Up here is my other gas, my H2S. These are some reactions that you should really sit down and know, and you should memorize them. Now what we'll do next time is we'll do oxidation reduction reactions. We'll go over what they mean and how to assign oxidation numbers, how to do simple half reactions, how to write net ionic equations with them. Thanks so much.